Let us move to our next question, question number 8. That is, if n factorial has 4 zeros at the end and n plus 1 factorial has 6 zeros at the end, then find the value of n. Let us see the solution of the given question. As n has 4 zeros at the end, it should have 10 raised to power 4 as a factor or 5 raised to power 4 as a factor. If we see all the natural numbers starting from 1 to have 5 raised to power 4, then the least value of n can be 20, 21, 22, 23 or 24. And n can be 21, 20, 21, 22, 23 or 24. Now further, we have that n plus 1 factorial must have 6 squares at the end, 6 zeros at the end. Now this is possible if n plus 1 is equal to 25, because there isn't any number less than 25 who has 5 zeros, 6 zeros at the end. So n plus 1 should be 25, or we can say that from here that n is equal to 24. Moving to our next question, question number 9. Find the least value of a for which the sum of the squares of the roots of x square plus a minus 2 x plus 1 minus a is equal to 0 is least. Now we have given that the sum of the squares of the roots. Now if we suppose that this roots of the given equation are alpha and beta, if the roots of the given equations are alpha and beta, then if the roots of the given equation are alpha and beta, then we have to find the minimum value of alpha square plus beta square. Now the minimum value of alpha square plus beta square may be given as minimum value of alpha plus beta's whole square minus 2 alpha beta. As we know that the sum of the roots, that is alpha plus beta, may be given as minus b upon a. That means the minus coefficient of x upon coefficient of x square, and alpha beta, that means the product of the roots, may be given as c upon a. So ultimately we have to find minimum of a minus 2 whole square minus 2 1 minus a. Minimum value of this expression may be given as minimum value of a square minus 4a plus 4 minus 2 plus 2a. That means the minimum value of a square minus 2a plus 2, or the minimum value of a square minus 2a plus 1 plus 1. That means the minimum value of a minus 1 whole square plus 1. Now as we know that the minimum value of a square function can be 0. A square function cannot have negative value, so the minimum value of a square function is 0. So the value of this, minimum value of this is 0. So the minimum value of this expression may be 1 only, and this value will be given at the value of a is equal to 1. So from here a minus 1 should be 0. That means a is equal to 1. Moving to our next question, question number 10. Question number 10 is given to us as in the year 2000 I will be old as the sum of the digits of my birth year. So tell when was I born. Let us try to find the solution of the given question. Now as I have given that I will be as old as the sum of the digits, so I can say that my maximum age is 1 plus 9 plus 9 plus 9, that means 28. Let the year of my birth be 19xy, so I can say that 2000 minus 19xy, that will be my age in 2000, and that will be equal to 10 plus x plus y, as I have given that in this in year 2000 I will be as old as the sum of the digits of my birth year. So sum of the digits of my birth year will be 1 plus 9 plus x plus y, that means 10 plus x plus y. So I can say that 90 is equal to 11x plus 2y, where x and y are digits from 1 to 9. So I can say that 11x is equal to 90 minus 2y, that would be greater than equal to 90 minus 2 into 9, that means 90 minus 18, that means greater than equal to 72. So I can say that x is greater than 72 by 11. From here I have that x is greater than equal to 7, where x is an integer and also x is even. Yx is even as 11x plus 2y is even. So to be this quantity even, 2y is already even, so 11x should be even. Now for 11x to be even, x should be even. So I can say that x is equal to 8. So 2y will be equal to 90 minus 88, that is 2. So y is equal to 1. So from here I have year of birth is equal to 19xy, that means 1981, that is our answer. Moving to our next sum, question number 11, that is given to us as the question number 11 is find all real solutions of the system of equations x plus y is equal to 2 and xy minus z square is equal to 1. Now to solve the above sum, let x, y, z be real numbers with x plus y is equal to 2 and xy minus z square is equal to 1, as we have given in the question. Then 4 minus x minus y whole square is equal to x plus y whole square minus x minus y whole square, that is equal to 4xy, that may be given as 4 plus 4z square. Thus we can say that x minus y whole square plus 4z square is equal to 0. Now as the sum of square of two quantities is 0, that means the two quantities are must be equal to 0. So this implies that z is equal to 0, also x minus y is equal to 0. From here we have the solution that may be given as x is equal to 1, y is equal to 1 and z is equal to 0. That is the only solution of the given. Moving to our next question, question number 12, that is given to us as let p of x be a polynomial with integer coefficients. Then prove that if p of x is equal to 7 for 4 distinct integral values of x, then p of x is not equal to 14 for any integral value of x. Let us have the solution of the given question. The solution may be given as, suppose that p of x is equal to 7. Now when x is equal to a, b, c and d, then p of x minus 7 is equal to x minus a, x minus b, x minus c and x minus d into q of x by divisibility theorem. Now if p of x is equal to 14 for some integer value x, then 7 is equal to x minus a, x minus b, x minus c, x minus d into q of x for that x. Now here we can see that RHS of the above equation contains at least 4 disjoint factors, that are x minus a, x minus b, x minus c and x minus d. But 7 has only 2 factors, as 7 is a prime number, so 7 has only 2 factors, that is 1 and 7, hence the preposition. Moving to our next question, question number 13, that is given to us as, question number 13 is given to us, show that 5 raised to power n plus 5 raised to power k can never be the square of an integer where n and k are positive integers. Let us have the solution of the above question. Since 5 raised to power n and 5 raised to power k both end with digit 25, so the last two digits of 5 raised to power n plus 5 raised to power k are 50. Now as we know that a perfect square number which ends with digit 0 should have an even number of zeros at the end. That means it should have at least 2 digits as double zero. Thus we can say that 5 raised to power n plus 5 raised to power k can never be the square of an integer.